Thanks to everybody for coming. It's an enormous privilege to introduce somebody who, as the cliche goes, should need no introduction, Tony Hoare, from his initial discovery of the quicksort algorithm, his work on the first Algol 60 compiler, his fundamental work on synchronization and CSP, and then his more recent work in unifying theories. He's contributed enormously, I think it's safe to say, to the field of computer science. Very happy to have him here from MSR Cambridge. One of the things that I think everybody has hopefully done before this meeting, and if not, should run out and do right after this presentation, is read his 1980 Turing Award lecture of the Emperor's Old Clothes, which is still every bit as remarkably true today as it was then. So, pleased to welcome Tony Hoare.
Thank you very much, John. It's a great pleasure and privilege to be here and meet so many of my new colleagues in Microsoft after a long career in the ivory towers of academe. The encouraging thing that I've found is that some of the work, much of the work that has been going on in the academic world is now coming to the forefront of practices in Microsoft and in other companies. And I would like to spend a little time to tell you the results of a survey which I conducted by email recently of how assertions are being used in current Microsoft practice. Let's see if I can... Oh, it's already happened. So why assertions? Well, I have to admit that to a large extent my choice of this title and topic is due to nostalgia. I first came across assertions in an article by Bob Floyd in 1968, and since then they have formed the cornerstone of my research into programming theories, programming semantics, programming languages, programming methods, and indeed even programming practice. They seem to me that they have achieved some degree of importance in practice today. My estimate is that perhaps 1% of Microsoft code, lines of code, are now assertions. So they're worth looking into to see how they are used effectively and perhaps how they might be used more effectively in the future. Because the practice of writing assertions is based on a programming theory, a theory which is closely allied to the principles of correct programming and defect avoidance, I think they have a great promise as a cornerstone of productivity tools which are currently under development and might be moving, and some of them have already been moved into practice in Microsoft with beneficial results. So, the great thing about an assertion is that it's used for many different purposes. It's used in test as a test oracle, in ship code for exception generation, defect tracking in RAID, compile time checking, program documentation, potentially even in proof. That was my research goal. It helps optimization. It helps analysis tools. They're used as preconditions of methods, postconditions, invariants, and for generating exceptions. I'll summarize each of those points in greater detail. The tool which uses assertions in their role as test oracle most effectively has been developed in the Office project. The keyword MSO assert is used to enable RAID to classify test case bugs in accordance with the assertion that it has the assertion which it has invalidated, so that if an assertion failure occurs, it's possible to check whether that assertion failure has occurred before, either recently or in the more distant past, and find out what was done about it. In some cases, maybe the same assertion fails twice on two different test cases, and this enables you to use twice as much data in tracking down what was wrong, and of course gives you twice as much benefit when you finally correct the bug. So the assertions, by classifying errors, similar errors together, gives a means of controlling the bug removal processes to a greater degree than is possible on a purely informal basis. In retail code, there are a number of different ways in which assertions are treated. In the VSEE development guide, there are three different macros suggested for controlling what happens in retail code. The VS assert causes the assertion just to be omitted from retail code. VS verify throw causes the assertion to generate an exception in retail code, and in VS verify a dialog comes up to enable the user to choose between those two options. I think there's a nice wrinkle on the VS assert macro, which requires two parameters, not just the assertion which is tested at runtime, but also a string which explains quite informally the reason why the developer thinks that assertion will be true when control reaches the point at which the assertion is placed. Otherwise, it's very easy to forget why that assertion was put in and why it ought to be true. When the assertion is in fact violated, it is possible for the developer to reconstruct the reasoning processes which led him to insert the erroneous assertion, and maybe instead of correcting the bug, correct his reasoning processes in a way that leads to the prevention of further bugs. So the explanation is helpful both to the writer of the assertion and obviously to its reader. If you look through the Office Watson RAID database, you'll see people trying to trace the causes of assertion failures where the reason for putting the assertion in has not been properly explained. The best kind of failures are those that occur early. Failures that occur during test are better than failures that occur on the customer site, but failures that are flagged before the test, i.e. at compile time, are the best of all. So one of my correspondents is using a macro to generate compile time asserts. The first line shows how the oops, I've got it wrong. Is a declaration of a dummy array that will cause a compile time failure if the assertion X is 0. It will declare a -1 array bound, or it will generate an assertion if the generate a failure if the assertion cannot be evaluated at compile time. So a compile time assert can only generate a report at compile time. As a result, it's only allowed to use it's only allowed to use functions and variables which are available to the compiler for evaluation. the benefit of the assertion lives much longer than the release of the first release of the code in which it has been inserted. The assertion remains as an integral part of the code, inseparable from the code, and it acts as a protection of the system against future changes. One of my correspondents is in the habit of putting very obvious assertions into the code to assert facts which, when the code is read, are obviously true at this point, but the assertion is motivated by the possibility that the code will be changed, it will be taken apart, that new instructions will be inserted, and the assertion thereby invalidated. Now, using assertions effectively in this mode is quite time-consuming, it's quite a commitment, and it requires some projection of how the code is likely to be modified in future releases. The same correspondent described to me how he would construct an error message which was triggered by a violation of the assertion, which contained instructions to the person who had just modified the code what other modifications he ought to be making in order to avoid this assertion violation. Not everybody has time to do that before their schedules expire. There's another use of assertions, which I call assumptions, or simplifying assumptions, which can be inserted into the code in the early test phases to assist in concentrating tests on the most relevant cases. There's a simple example I've shown in the second bullet point here, where in early test, when the objective is to check the overall viability of the change or the new feature, it's useful to postpone the treatment of exception cases. So the assertion is really a simplifying assumption for this test run of the code, so that if the test case violates an assumption, this really means that the test case has been a little bit too searching than what I would have preferred on this test run of the code. So it's not really an error in the code, it's just an indication that the test case is not, it's doing its job properly for the eventual ship code, but we want to ignore the test case rather than correcting the code at this stage. So failure of an assumption test means that the test is irrelevant to the current development needs. Now, I think the most effective extension of the role of assertions, as Bertrand Meyer described in his talk yesterday, is to assert the data rather than just the code. An invariant is an assertion which is true of, shall we say, every object of a class before and after every method call. So an invariant of a class plays a double role. It's simultaneously a precondition of every method of the class, in that the writer of the method can assume that it's true before entry. It's also a postcondition of the class. The writer of the method has the obligation to make it true again after exit. One of my correspondents makes a general practice of declaring the class invariant as a Boolean function local to the class itself. So in a class that manipulates a circular list, the class invariant may be a Boolean function which contains a check that the list is circular, for example, if that's the invariant on which this particular implementation of the lists depends. In the new program analysis tool prefix, there is a special kind of assertion called prefix assume, which is an instruction to prefix to assume the truth of whatever assertion follows it. And on that assumption, prefix can avoid generating noisy reports of potential errors. So, for example, if the code wishes to find something in a list and assign that to a pointer, the function find is defined to return a null pointer if the something is not in the list. So but the programmer happens to know that he just put that very same thing into the list, but somehow or other prefix didn't detect that, and so the programmer puts into the code a prefix assume, which tells prefix that the pointer is not equal to null, and then, of course, should jolly well have an explanation of why the programmer thinks that that assertion is true. The Visual Studio C compiler, VC and VC++, I think, do also take account of assertions in the form of assume statements, which are instructions to the compiler to assume some fact which may be useful for optimization. One of the useful facts for optimization is some kind of assertion that two pointers or references don't point to the same object. In fact, the assertion that the compiler is pre-programmed to recognize and take advantage of occurs in just this particular case. Assume false indicates a path that the programmer believes can never be taken, because false can never be true. So if assume false is put in the one of the cases of a switch, particularly the default case, it can tell the compiler that there's no need to emit a default code for this case. If the other cases exhaust all the possibilities, for example, false and true, then there's no need to emit a default case. Well, Bertrand yesterday talked about contracts and how contracts consist of preconditions on method calls and postconditions on their results. The precondition is an assumption as far as the writer of a method is concerned. It's an assertion as far as the caller of the method is concerned. And the fact that the caller is picking up the obligation to make that precondition true is what justifies the writer of the method in assuming that it's true before the body of the method is invoked. Here's an example illustrating three different kinds of assertion in a single method. The insert method is designed to insert the node passed as a parameter into a list. That const, I'm afraid, is incorrect. The entry assertion, which is the precondition, states that you mustn't try to insert a null pointer into a list. and that's an obligation on the caller of the method. The object assertion is the class invariant, which it's an obligation on the implementer of the class to make true after every method call. And a simplifying assumption is that perhaps that the node is not already in the list, which, of course, eventually is going to require special treatment, but for the time being, the programmer wants to run a test in which such a violation of the assumption will reject the test rather than the program. Yes, a question.
The object assert, is that actually something that somebody, one of your friends uses?
Yes.
So I take it this insert is a method of a C++ class, and that this object assert has then some relevance to that particular
Yes.
object. This.
I think this text, if I've copied it correctly, was contributed by a colleague in Cambridge. Object assert is a macro, which has the same effect as an ordinary assert. The class invariant is the Boolean function which codes the invariant, which should be true before and after every call. So it's really just an ordinary assert, but being flagged as an object assertion just to indicate that this is an invariant rather than an entry assert, which is a precondition.
This is going to be compiled, a macro, into some object whose lifetime is the method, and it has a constructor which checks the invariant and a destructor on exit. So that class invariant is going to be checked at 2 points in the code.
That would be a very good idea. But in fact, he writes the object assert at the end of the method as well.
Oh, well,
so
plus you don't. Okay, the
nothing very
implementation detail. You don't actually have to do that.
Good.
I think you can probably compile that into something. Okay, but the intent is that an object assert is so the. I'm trying to understand what's the difference between that and just the plain assert. You're saying if he inserts it at the end, then there's really no difference between object asserted, except it has.
I think that's right. I think the point that he is emphasizing, and a point which I too wish to emphasize, is that assertions play many roles, and you can see from the number of different notations which different people have used, or even the same person has introduced many different notations, just to remind themselves of the different roles which the assertion is playing in their code and in their testing. So I report what I am told. It appears I don't always quite understand it. Thank you very much for deepening my understanding. Here's the same class invariant method being called as an object assertion, an invariant assertion, at the end of the same piece of code, coupled with an exit assertion, which says that the n, this slide is a continuation of the method which I started on the previous slide. So the ... here is a stands for the body of the method. The exit assertion again calls a method of the same class to indicate what the user of the method can expect when the insert method has completed its work. These two assertions are, of course, an obligation on the method writer to guarantee. The specification technology using preconditions, postconditions, and invariants has been described well by Crispin Goswell in the COMAPS group for describing COM interfaces and types. It's needed when components are plugged together in unusual or in highly flexible ways to make sure that not only the syntax of the connection, that is to say, as it were, the physical pins of the plugs that connect the components together, but also the behavioral semantics of the communications and interactions that go along those wires. Those too must be compatible, as indeed they must be in the design of electronic and assembly of electronic components. So a careful specification, including the use of assertions, helps to control dependencies between components. An early formulation of the assertions helps to encourage simpler interfaces between the components, simpler APIs. The fact that the assertions are placed on the external interfaces of each component links directly with the use of the assertions as test oracles in test harnesses. And again, a well-placed assertion, a well-formulated assertion, a strong assertion is good for the user of the component and its implementer alike. So, assertions have many uses. Different development teams and different developers have discovered and exploited these different uses. They've given them different notations, and they've written different tools to exploit their understanding of the use of assertions. I would like to suggest, if there's one message that you're going to take away from this talk, is that assertions are a multipurpose device, and that the real payoff comes when the same assertion is used many times in different roles at different phases in the development of a project. So, the lifetime of an assertion. Let it be born as soon as possible. Let it be born already in the initial discussions of a possible feature or product. The assertion, I use the word assertion to stand for the Boolean condition that is eventually going to be a test of the observable behavior of the delivered product. So it's the Boolean condition rather than a particular assert statement that I'm talking about. The same Boolean condition can be raised as a discussion point to analyze the possibilities of the right in the earliest phases of the design of a product. Then, if the discussion is favorable, the assertions then becomes a decision on some of the properties that the product is going to exhibit. It is then used to allocate tasks between different parts of an implementation, whether they are actually delegated to different developers or not. It's at the task allocation stage that the important decision is made as to which assertions are to be used as assumptions and which are to be used as postconditions or commitments. Because the central rule in splitting up a complex task is that each subtask may rely on certain assumptions, provided those assumptions are validated as commitments by other parts of the task. So in splitting up the tasks of a complex job, assertions define the interfaces between the tasks even before the implementation has started. It's at this stage that they can begin to be used in the design of a test oracle, to design of a test harness to check at unit test that each component, each subtask, is meeting its obligations. The developer on initial tests puts the assertions in to some extent as a hypothesis, as a hope, rather than as a guarantee. But when the developer is confident that that this segment works, the assertions should be perhaps visited again to check that the the developer is willing to sign off that that assertion will be true. Because it's only on assertions in which the developer is extremely confident that they will be true, not just now, but for all time, that it is possible to take an assertion as a compiler hint for optimization purposes. Then, however confident the developer is, and the more confident, the more important it may very well be that at least some of the assertions remain in the ship code as generators of exceptions. Generators of long stop exceptions that cause the service to the customer to degrade gracefully rather than leading to an unknown crash which one believes is very likely. The more certain you are that the assertion is true, the more likely it is that you have built that into the very fabric of your code, and so the more likely that an assertion violation is a precursor of a very much worse crash. Yes, question?
How do you do that when the end user is Dilbert's pointy-haired boss? You can tell an engineer the compiler has hit an inconsistency. That boss can't spell inconsistency. So what happens if he runs Word and he gets an assertion that requires logic?
Are you referring to the phenomenon that the customer sees on the screen? This should never happen. If it does, connect Genie on the extension number, something like that. Yes, many of my correspondents have told me about that. Yeah, okay, please don't write assertions like that. Yes?
Actually, a related question. You can take assertions to sort of the self-checking sort of code extreme where you actually, in an assert, call a function that does some very complicated check. What is your view on sort of how complicated asserts should get or can get, or where does the complexity of the code in the assert become sort of a detriment because it itself is subject to error?
You're right in pointing out that there is a scale. I can't tell you where on the scale to put the cutoff point. Every assertion requires judgment to decide how long to keep it as an actual test, whether to keep it in the ship code, and possibly some development teams might have have a management procedure for deciding whether assertions should be retained in ship code or not, or at least a developer would ask a friend to take some responsibility for removing an assertion from ship code. And obviously the argument that it's jolly expensive to test would be one of the reasons for removing it. I think quite a lot of developers are surprised to find how little time the assertions are taking. 5% is a figure that's been quoted to me fairly often. This is probably because the main assertions that are left in the code are preconditions, and preconditions on the whole tend to be much simpler than postconditions. Oh, good. Who are we?
Comment possibility and feasibility of use of assertions in multi-threading applications, for example, for avoidance of possible deadlocks among communicating persons, or on the other side, danger of inducing deadlock if assertion would be on the other side.
I think that this is absolutely crucial, and the extension of the use of assertions and to the concurrent programming environment and to questions of concurrency safety has been a subject of my recent research, and I think and of the research of many of my colleagues in Microsoft Research. I think in a way the research problems of assertions in sequential code are pretty well understood. I mean, they don't exist anymore. This is a non-research technology, perfectly safe to deploy in practice. But extending this to concurrency, I'll mention it again later in a later foil. but I'm afraid I will only mention it to say still a subject of research. Yeah?
My comment is more mundane. It's also quite unethical in the sense that for this business of assertions in shift code, as a manager, I would want to lie to my developers. That is to say, even if I'm intending to leave assertions in shift code, I would never tell them, because any excuse to lower your guard as a developer is dangerous. So I might lie to my developers, tell them there's not going to be any assertions left in the shift code, and then at the last minute, I might still leave them in.
As always, Bertrand, you can give a better talk than I can. A lovely point. Thank you. Could everybody who's listening on distant monitors hear that question? Bertrand Meyer says that he uses a noble lie to tell his programmers that the assertions will be removed in ship code, and then he quietly disables the removal on his compiler so that they do in fact get shipped, as exception generations, of course. But the one place that you must never, never remove an assertion from is the program documentation. The legacy code that you leave for subsequent development by yourself and by other people must have the whole history of every assertion retained in it for all time, because assertions go on delivering value again and again in subsequent releases of the code. That's my message. I'd now like to move on to what I have discovered about interesting work that's going on in Microsoft at the moment to improve programmer productivity practices, and in particular to reduce defects. One of the projects is a Six Sigma project attempting to reduce defects in designs and implementations on the analogy of similar projects which have been successful in large engineering companies. The basic tenet of Six Sigma is that defect reduction does not cost. Defect prevention pays for itself over and over again, because the cost of remedying the defects, even when you do it, is just too high. So almost any effort that can be put into defect reduction is going to pay off on the bottom line. Do not stint on the effort needed to improve coding quality and engage in any managerial or technical practices which are going to reduce bug counts at all stages in the development process. Now, one of the recommendations of the Six Sigma project, one of their 6 recommendations, is to write the unit test first. And there's quite a lot of evidence that this is an extremely successful way of reducing bug counts. In other words, you write your tests to be as rigorous and exhaustive as possible, and having done that, you realize all the possible mistakes you could make, and that realization alone enables you to avoid nearly all of them. I heard a lovely story in Nortel about 10 years ago. They're in the business of delivering program-controlled telephone exchanges, or offices as they call them. Their customers were getting annoyed at the number of bugs that were shipped with new software, which they had to report back. And so they decided they were going to follow this advice and really test their code extremely rigorously. And they designed all their tests in advance, so they knew what they were going to do. And it worked. The product was delivered on time, and the customer was entirely happy with the greatly reduced number of bugs. So there was no need to tell the customer that in order to meet the scheduled delivery dates, they hadn't actually had time to run the tests. But rigorous testing, and I think this is going to be rather a general point I'll make now, rigorous testing and indeed the rigorous formulation of assertions is going to require inserting into your code, in the test harness mode at least, extra code, extra variables and extra assignments to those variables. Because these variables are used only in assertions, I'm going to call them assertional variables. I'm going to declare them by assertional declarations. My foil shows an example of a double array, A0, of the same size as some parameter A, which is initialized to hold the initial value of A. Then perhaps the method does some kind of rearrangement of A, perhaps it sorts it, and the exit assertion checks that the final value of A is a permutation of A0. An essential component in the correctness of the method. Of course, that assertional variable is really quite expensive to set up and test, but it can be sliced out of the retail code using normal slicing techniques for discovering and eliminating dead data and declarations. So the view I have of the specification of a program is the same as the view I have of a test harness. We do not specify that the program, we do not state that the program is correct as it is shipped, as it is run on the customer site. What has to be correct is what I call an instrumented program, a programmer that has assertions put in at crucial interfaces between its components, which has additional storage and additional assignments made in order to reflect what that program is intended to do, side by side and synchronously with what that program actually does. And it's the fact that this test harness, which is really the specification of the program, the fact that the test harness, which has been designed by all possible means to make that program break, the fact that that test harness does not break the program, that gives you the confidence that the program will work on the customer site even after the test harness has been removed. This is entirely by analogy with engineering practice, where an engineering assembly, say a jet engine, is placed in a test assembly on the laboratory bench. Well, in the case of a jet engine, rather a large laboratory, and they put instruments on every measurable point inside that test engine. They do not run that test engine until it crashes, until the blades fly off, I promise you. They put measurers of every possible thing they can think of that will go wrong: vibration, heat, tensions. Anything that is measurable is measured. And on everything that is measured, they place tolerances. They believe that the assembly will be okay as long as the temperature, or whatever the measurable, does not exceed the stated bounds. In the same way that we believe that the program will not crash provided it passes all its assertions. Then, of course, the Six Sigma philosophy is tighten all the tolerances. If you are allowed a variation of 3 volts, bring that down to 0.3 of a volt. Just for the sake of it. You don't know whether the product is going to improve. You just do it in order to make it more likely that you will detect incipient errors on the test bench rather than serious errors in the field. If this analogy holds, then the corresponding actions that we should take in test harnesses is constantly strive to make the assertions stronger. Stronger assertions, ones which place tighter constraints on the interfaces, make the program more deterministic, more predictable, and, well, as an act of faith, one could believe that that will make the delivered product more robust. Now, these extra variables that are added into the code do not have to track exactly the whole behavior of the code. They can, if you wish, just track certain the structural integrity of the code, tracking such states as the allocation status of storage or of other resources, of locks, checking that actions are permitted only on locks that are in fact held by the program, and checking that locks that are held are released, locks that are released have been held. Very simple Boolean variables can be introduced to represent the important structural aspects of the behavior of the program. So you can declare an assertional variable, let's call it a capability set, holding the set of permitted actions. Every action then has to be preceded by an assertion that that action is in the capability set of the current thread. Certain actions, closing actions, release actions, are defined to decrease the capability set, and certain of them to increase it. And tools are being developed to reliably insert these extra variables, these extra actions, and these extra assertions in order to make sure that code conforms to its specification. These ideas have already been featured in a tool being developed for test case generation called Utah Lite by Jason Taylor in IE, I think. It's called model-based testing, and it abstracts the desired behavior as a graph in which the nodes stand for states of the checker, or in fact states of the program, and which the edges of the graph represent the actions that take place when the program and its model move from one state to another. These abstract graphs, these edge-labeled graphs, are then used to generate test scripts in large numbers, because a test script is nothing but a list of the actions occurring on the arrows of some path in the graph. So the interactive tool is able to generate paths, action paths to order, like please generate an action path from this node to a node which satisfies this assertion, or a node which fails to satisfy this assertion. And that restrictions can be put on saying paths less than 10, or print only the shortest path, or print a random path, or print a path that visits each action at least once and each node at least once. These are then run on their multi-machine servers to check the conformance of the programs under test. Now this is the kind of test harness which I would like to see, and I think is already beginning to be generated in advance of the writing of the code, perhaps in consultation with the developer and the program manager, to check that the abstractions are indeed the relevant ones for the correctness of the behavior of the code. The graphs that are used for practical testing in a test harness tend to be very much simpler than the state of the whole machine. They only abstract certain Boolean variables, simple abstractions from the state of the machine. But the same kind of technique can be used conceptually to talk about highly large abstract variables, perhaps ranging over mathematically abstract structures like sets and mappings and sequences and combinations thereof. Such abstract entities can be specified in an abstract state machine language, which is currently implemented. And a successful use of the abstractions enables one to specify the intention of a piece of code or the intention of the machine that lies behind a human interface certainly more clearly than the actual bits and bytes of the store of the computer, which will be implementing that abstraction. Now, once the abstraction has been formalized in this language or some other, then it is possible to start analyzing it and executing the abstract behavior of the code even before the code has been written. This language has been applied as tests evaluated by application to COM components, and the project as a whole is led by Yuri Gurevich and his team in Microsoft Research. Flitting back to more immediately practical problems, what do you do about putting assertions into legacy code? There are millions of lines of it, and it's mostly unasserted. Can we generate assertions automatically and put them in legacy code to guide any future upgrading and the insertion of new features in that same code? There's been a recent doctoral thesis submitted by Michael Ernst to the University of Washington, which uses execution tracing to help to discover likely assertions from data collected in test. This, of course, is completely useless in finding assertions that the program under test actually violates, because by definition, every assertion it generates will be true of the code under test. But the purpose of these assertions becomes apparent as soon as that code is modified, because any assertion that is violated by the modified code is a potential anomaly. It may indicate that the change violates some assumption of the original programmer. It also gives you some estimate of test coverage. If you find that a variable that you've lovingly introduced into your program for some useful purpose only in fact ever takes the value 0, then probably that wasn't what you intended. So dead variables can be detected by this. Or if it only takes 3 values and you were expecting it to range over all the integers, then something has gone wrong, obviously. So tools like this, I think, might come into use for dealing with legacy code. Going back to the sort of rational construction of code, the theory that programs should be developed from their specifications, there's a project at Compaq led by Greg Nelson, which has delivered recently for academic use a tool which does extended static checking of Java programs. And that uses deductive techniques, mathematical logic, to generate verification conditions, which it then uses a theorem prover to try to prove. The point about assertions, and the point that first attracted me to do research on assertions, is that in principle, if your assertions are strong enough, it is possible to prove that they will always be correct when the code is running. And obviously any program that you've actually proved by mathematical proof that the assertion will always be satisfied, there's no real reason to test that assertion. It's if your mathematical proof is sound, then it's impossible to invalidate at a runtime. So Greg Nelson uses a theorem prover to check the soundness of the assertions. Of course, theorem provers aren't all that powerful now, and the checking of them does depend on that the assertions too should be rather stronger than most assertions that people actually write in their code. So Rustan Leno, who's a member of Greg's team, has started a project for automatically strengthening the assertions in the code. It's a curious technique. He generates random assertions, and then he uses the static checker to see what combination of random assertions leads to a verifiable code. I don't know that I altogether believe that's going to be the most efficient way, but his heart is in the right place. The technique of building and using an abstract state machine or a graph model of the behavior of programs is being promoted in a project called on a tool called Vault, conducted in Microsoft Research here in Redmond, which is a tool that helps to interleave the extra variables and assertions into the code of the test harness, and then uses model checking or verification techniques to prove that all the assertions will be validated. Now, because the language in which the extra variables are declared is very simple, very restricted, and because the actions on those variables are very limited, it is possible the decision procedures which are used to validate the assertions are capable of checking that they will all be true. So the ideal of being able to check assertions by proof, which was the motivation of many years of my research, is beginning to bear fruit, only of course, for highly abstract, highly simplified models of the program behavior. The techniques for finding proofs and finding bugs use the method of exhaustive search, highly optimized and highly accelerated exhaustive search. And Daniel Jackson at MIT has developed a language, a relational language for expressing the specification of perhaps even non-deterministic programs, concurrent programs, for example. And he uses the constraint solver, a Boolean logic program, for finding counterexamples to the specification. The trick is that he reduces a specification which mentions variables with an unbounded number of states or a very large number of states. He considers all possible cases in which the actual number of states needed, of values of these variables needed to exhibit a counterexample is highly limited. So the kind of guarantee that can be given by Jackson's relational checker is that if there exists a counterexample, a case which breaks this code, which involves less than 4 objects of this class, and less than 4 objects of that class, and less than 5 values of this counting variable, and less than 7 actions of this kind, then the constraint solver will find that counterexample. In other words, if the counterexample is going to be small enough that I can understand it and do something about it, then the constraint solver will find it. Of course, we do know that there are errors which really require 14 or more steps before they're revealed, and this tool might give you false confidence in avoiding that kind of error. Another project that's going on in Microsoft Research is also based on the abstract modeling technique, automatically validating temporal safety properties of interfaces. It goes to the extreme of restricting the model variables to be only Boolean variables, so that there are at most two cases to consider. It uses non-determinism in the model to represent aspects of the behavior of the system which cannot be encoded in the very simple abstraction that's used. And then it analyzes the program in such a way as to guarantee that the model exercises every possible path in that program. So there is a very simple model that is guaranteed to track every possible path in the program. And then by putting assertions on the model, it's possible to track those paths that lead to error, and therefore it is possible to give a guarantee, if such paths do not exist, that the error cannot occur. Concurrency safety. Yes, we get on to that question, and as I promised you, I would have a foil which raised the issue, and then say, I'm afraid that's the subject for another talk. What I hope to do before my next visit to Redmond is to conduct a similar sort of survey of development managers to find out the practices that are currently in use and recommended for avoiding concurrency errors, for avoiding deadlocks, race conditions, and for making the code concurrency safe. And if I'm successful in that, perhaps that will be the subject of my next talk. So finally, I must give my heartfelt thanks to everybody who's helped me find out the information that I've been reporting back to you. It's nearly all been gleaned from email contacts and personal conversations on this recent visit with some wonderful people, inspiring people, who've really taught me a great deal about my favorite subject, which is assertions. Thank you very much.